Did you know that the existence of a planet beyond our familiar reach, located just 4 light-years from Earth, has long been a prime target for those searching for extraterrestrial life? That planet is Proxima Centauri b. It lies within the habitable zone of the Alpha Centauri star system. But could we actually live there? The challenges humanity would face are not limited to engineering or science alone, but to a constant struggle against forces from the universe that we cannot fully predict. We are confronted with the most fundamental philosophical questions about life and existence. If a planet like Proxima Centauri b could serve as a cradle for new life, could we adapt to conditions entirely unlike those on Earth? It is a place we never believed we could reach. And yet it is where we begin our journey into the harsh reality of Proxima Centauri b. Proxima Centauri b, a jewel nestled within the Alpha Centauri star system, is a destination for boundless aspirations, but it is also fraught with unforeseen dangers. The Alpha Centauri system, with its 3 stars weaving a cosmic tapestry that never sleeps, is anchored by Proxima Centauri, a red dwarf star. Small, yet astonishingly long-lived, that serves as the host star of this distant planet. Unlike our brilliant sun, Proxima Centauri is dimmer. But it possesses a strange and remarkable trait: its ability to sustain life over an extended period, even long after our own sun has burned out. The only planet within the habitable zone of this red dwarf might represent humanity's next great leap. That lies within the habitable zone, the region where liquid water could exist. A key factor that makes Proxima Centauri b a promising candidate for extraterrestrial life. But does this truly translate to the possibility of human survival? Is this the paradise we seek, or is it merely a lifeless world shattered like a distant, unreachable glass pane? Proxima Centauri is a red dwarf star, cooler and smaller than our sun. Yet it boasts a lifespan hundreds of times longer. This means that if Proxima Centauri b truly can support life, it could maintain a stable environment for millions of years, outlasting the harshness of younger stars. So, can life thrive here long-term? Or will our existence be but fleeting moments in an infinite universe? Imagine stepping foot on a planet beyond Earth, where the concepts of life and death are no longer what you've known. Can humanity survive here, in a world where familiar conditions like energy and atmosphere no longer hold the same meaning? Proxima Centauri, the host star of this planet, emits only 0.1% of the light our sun provides. Though it seems faint to us, this light is the lifeline for Proxima Centauri b. To survive, this planet must orbit perilously close to its star. As if caught in an irresistible dance with an unstoppable force. But what no one expects is that this close proximity doesn't just provide the energy the planet needs. It also introduces a deadly environment filled with hazardous radiation. The radiation bursts from the red dwarf, unpredictable energy discharges, could strip the planet's atmosphere away, dismantling the fragile foundations of life. Imagine a planet with no protective layer strong enough to shield against ultraviolet rays and continuous radiation blasts from the red star. It's the cruel irony of the universe. A planet that has the potential to support life could be the very place where that life is most easily lost. And what about the atmosphere of Proxima Centauri b? Is it even breathable? The answer serves as a cautionary tale. The planet's atmosphere is thin, containing very little carbon dioxide, methane, and nitrogen, essential components for sustaining life as we know it. Its atmosphere is not only fragile, but also incapable of trapping enough heat, causing the planet's temperatures to swing drastically. From -40 degrees Celsius to 30 degrees Celsius, humans would face skin-piercing cold or scorching heat, akin to being inside a vast furnace. This isn't just a survival challenge. It's a question of humanity's very existence. Can we endure these harsh conditions to continue? Or will we be a fleeting ripple in the vast, indifferent cosmos? When everything seems hopeless, when the radiation from the red dwarf Proxima Centauri is attacking every cell in your body, when the fragile atmosphere of Proxima Centauri b is not enough to shield you from the harsh effects of space, there may be only one hope left to sustain life: the Terminator Zone. But is this the last chance for humanity, or is it merely a temporary refuge, full of danger and waiting for inevitable failure? The Terminator Zone, a name that seems mysterious, is the region between the daylight and night sides of Proxima Centauri b, where the transition between light and darkness never truly ends. It is a twilight zone, neither fully day nor completely night. In this area, the temperature remains more stable than at the planet's extreme poles, where the sun shines eternally, or where darkness never relents. The deadly heat of the daylight side or the bone-chilling cold of the night side cannot penetrate the Terminator Zone, making it the last possible place where life could thrive on this planet. So, can humanity establish a foothold in this area? Could the Terminator Zone become our second home? Or is it just a temporary hiding spot amidst the inevitable cosmic disasters waiting to strike? Scientists argue that the Terminator Zone may harbor water, the essential element for life. Water, the magical liquid without which life on Earth cannot exist, could be hidden in the planet's cracks, waiting to be discovered and utilized. But can life truly survive in a place so fraught with peril? Where water might only be an illusion, the air is scarce and radiation could strip away everything? Imagine that humanity has set foot on Proxima Centauri b, a distant planet in the Alpha Centauri star system. Imagine that we, fragile beings from Earth, have crossed this vast cosmic expanse to seek a new world. But can we truly survive in a completely alien environment where every familiar rule of life is upended? Can we navigate and endure in a space filled with dangers we've never even imagined? Proxima Centauri b is nothing like Earth. And the challenges begin the moment we arrive. One of the biggest hurdles is space itself, the space we've always taken for granted, now transformed into a maze of confusion. With no sunlight to guide us, no blue skies to orient us, we are lost in the shadow of a distant star. Proxima Centauri b orbits so close to its host star that it only receives a faint, dim light, like a tiny flicker in the vast, unending night. There are no familiar constellations, no guiding signals to lead us, only a thick, oppressive darkness. What will we do when we can't see anything but a foggy world before our eyes? However, an even greater danger lurks ahead. Ultraviolet radiation. Proxima Centauri, the red dwarf star that governs this planet, emits a kind of radiation far stronger and more dangerous than anything we experience on Earth. These ultraviolet rays are nothing like the sunlight we know without the protection of Earth's ozone layer. These rays would not only harm our health, but could also penetrate our cells, destroying DNA and exposing humans to the risks of mutations and cancer. Without special protective measures, the radiation from Proxima Centauri could quickly make any attempt at survival on Proxima Centauri b unsustainable. Proxima Centauri b, the closest planet to Earth, just 4 light-years away, has become the focal point in the search for extraterrestrial life. While it seems promising, we still don't know if the atmosphere of Proxima Centauri b can support life. Scientists typically use transit spectroscopy to study the atmospheres of exoplanets. However, for Proxima Centauri b, this method cannot be applied due to the planet's lack of conditions that would allow us to study its atmosphere through starlight. If the atmosphere of Proxima Centauri b is too thin to shield us from the dangerous radiation of Proxima Centauri, can we truly endure? A planet without this protective layer could be a barren wasteland, making settlement an insurmountable challenge. However, if Proxima Centauri b does have a sufficiently thick atmosphere and the right temperatures, it could support liquid water. Water, the essential ingredient for life, becomes our one glimmer of hope. If the conditions are right, water could exist somewhere on this planet, providing the foundation for life to flourish. But is that really possible, or is it just an illusion, a fleeting dream in the vastness of the infinite universe? Proxima Centauri b is a planet brimming with potential, yet it is far from without its dangers. Humanity would face serious challenges if we set foot there, from the intense radiation of Proxima Centauri to the fragile atmosphere that cannot protect us from the harsh elements. Life in such an environment would become an unceasing struggle, where every moment of existence is fraught with risk. Water, the essential building block of life, may exist, but it would be as fragile as a dream, barely graspable in the infinite expanse of space. Despite these formidable challenges, Proxima Centauri b remains a promising destination. This planet, with its hidden conditions, could hold tremendous opportunities for discoveries about life beyond Earth. While the obstacles are numerous, each step we take toward understanding this world brings us closer to the possibility of surviving in a completely alien environment. This universe is full of questions and opportunities. Proxima Centauri b, despite its dangers, is one of the great questions humanity cannot afford to ignore. Can we overcome the challenges to survive and thrive on a distant planet? Or will life there remain nothing more than a fleeting dream? The answer is within reach, in the first steps of our grand journey to explore the vast expanse of space. Since the Big Bang gave birth to the universe around 13.8 billion years ago, space has been expanding like a kite pulled taut by the wind, carrying hundreds of billions of galaxies drifting ever farther apart. Thanks to Hubble's law, we know the universe is expanding, and doing so at a staggering rate. In this vast cosmic canvas, our Earth, orbiting an ordinary star called the Sun, is but a tiny speck of dust floating in an endless ocean. Although astronomers have mapped out regions stretching 45 billion light-years, much of the universe remains a blank haze, unseen, unexplored, only dreamed of. Yet within this void, one star system draws particular attention. Alpha Centauri, the closest stellar system to Earth. Just 4.24 light-years away. Alpha Centauri is not a single star, but a triple star system. Two of them, Alpha Centauri A and Alpha Centauri B, are sun-like stars orbiting each other in a celestial dance lasting decades. The third star, Proxima Centauri, is smaller and dimmer, orbiting far from the pair, and it is actually the closest star to Earth. Proxima Centauri is the nearest star to our Sun, while Alpha Centauri A and B form a close binary pair. We are looking at a star system with a familiar structure, with planets located in the habitable zone, the ideal conditions for life to emerge. In 2016, humanity first detected signs of a planet quietly orbiting the star closest to us, Proxima Centauri. Since then, 3 exoplanets have been discovered: Proxima Centauri B, C, and D, dark gems hidden in the faint light of a red dwarf star. Proxima Centauri B is a strong candidate for life. It lies within the Goldilocks zone, the habitable region where temperatures are just right for liquid water to exist. With an orbital period of just 11.2 days. A year passes here in less than 2 Earth weeks. Its host star, Proxima Centauri, is a tempestuous red dwarf, frequently flaring with intense radiation and stellar winds up to 2,000 times stronger than those of the Sun. These magnetic storms could strip the planet's atmosphere, unless it's protected by a magnetic field as strong as Earth's. So what if life does exist on Proxima Centauri B, shielded beneath a magnetic barrier? Imagine a civilization thriving under dim red light, with organisms whose skin absorbs infrared light instead of white light. Their skin might be metallic black, red, capable of absorbing and converting infrared light, much like plants on Earth harness white light. Some creatures may be bioluminescent, forming networks of light in the darkness. Their eyes may be large and multi-layered, adapted for seeing in darkness and detecting radiation. Some may even perceive magnetic fields and wavelengths invisible to humans. Their bodies could contain biocrystals that reflect radiation, natural shields against stellar flares. They may communicate through emitted light, blinks, color changes, or intensity shifts corresponding to words, emotions, and tone. Their cities might be built deep underground or in massive caverns, using insulation and radiation-reflecting materials. On the surface, only observatories, power towers, or signal centers remain, shielded beneath giant magnetic domes that manage intense radiation. They may have engineered a planet-wide magnetosphere using giant magnetic cores, pulsing hearts of artificial field generation. Due to the dim light, they wouldn't rely on solar energy, but would harness power from gravitational shifts and cosmic radiation. Their spacecraft may not be metallic, but biomechanical life forms, capable of surviving space, self-repairing, and sensing space-time. Unlike Proxima b, Proxima c lies farther out, beyond the habitable zone, a giant planet, possibly icy or gaseous. Temperatures here are frigid, and the light is dim, like an eternal twilight. With only about a quarter of Earth's mass, Proxima d is likely a small rocky planet, orbiting very close to its star, perhaps too hot and harsh for life as we know it. But if beneath its barren surface lies a network of caves shielding it from radiation, could microbial or even intelligent life have evolved underground? In 2020, while humanity was grappling with the global COVID-19 pandemic, a mysterious signal from space quietly stirred the astronomical community. The signal, named BLC-1, was a radio wave sequence detected by the Parkes telescope in Australia, coming from the direction of Proxima Centauri, the red dwarf closest to Earth. It wasn't a gamma burst, X-ray, or typical radio noise, but a fixed, prolonged frequency. Steady and undrifting, unlike any natural signal. Its characteristics were chilling, stable, distinct, and seemingly intentional. Experts immediately ruled out satellites or human-made interference. It didn't match any known natural phenomena. Uniquely, BLC-1 did not repeat, as if it came just once, then went silent forever. But if it was random, why from Proxima Centauri? where habitable planets are under intense scientific scrutiny. If not by chance, could this be a signal from a distant intelligence? Testing whether we are listening? And if one day we reach Proxima Centauri, not by spacecraft, but through thought, data, and the gaze of our telescopes, then every thought, every question, every story like this will have been our first steps. We tell stories of unseen worlds not because we know what awaits, but because the desire to explore is instinctual. The universe is vast, cold, and indifferent, but maybe it isn't. Maybe, somewhere out there, a pair of eyes is also gazing back at us, wondering the same thing. Is anyone else out there? Giant ecological structures rise, protected by massive domes, where humanity steps into a space beyond the reach of imagination. After a long journey, humanity has found its new home under the light of Proxima. Welcome to Dawn Colony. Our space travel technology is not just a simple step forward, it's a breakthrough. Advanced spacecraft have carried us to a planet once only dreamed of. But the true wonder isn't just setting foot on Proxima b. It's the call from the universe, inviting us to uncover mysteries yet to be revealed. Proxima Centauri b, with its thin atmosphere and unpredictable temperatures, is a chaotic world. Yet it's also one where humanity can survive and regenerate under the cold, distant light of the red star. Dawn Colony is not merely a place to start over, it's a realm where everything can change. This is not a simple journey, but a turning point in our eternal quest, where humanity faces challenges that science has yet to explain. Can we master this world, or will we remain wanderers in a strange land, swept into a universe full of unanswered questions? Under the strange red light of Proxima Centauri, Proxima b appears as a distant alien world. To adapt to this unique environment, red light nurseries were developed, where specially chosen plants thrive under Proxima's spectral light. These areas are designed to harness the full potential of the red spectrum, ensuring crops grow vigorously, even though the light here is unlike anything we've encountered before. But it's not just the light that presents a danger. The ultraviolet radiation from the red dwarf star could be deadly, requiring humans to wear specialized protective suits to filter out these harmful rays. These suits allow them to survive in an environment that bears no resemblance to anything we've known on Earth. One of Proxima b's most peculiar features is its tidal locking, which means one side of the planet always faces Proxima, while the other remains in perpetual darkness. This creates a perpetual twilight zone, where temperatures remain temperate, a perfect setting for the Dawn colony to thrive. Beyond this twilight zone in the eternal darkness lies an uncharted realm of mysteries yet to be revealed. Perhaps eternal ice, underground reservoirs of water, or even geothermal life forms. These dark regions may become key areas for research and resource extraction, where geothermal energy and artificial light sustain life. Who knows what might lie hidden in that darkness? Could it be forms of life never imagined? Or small worlds filled with unimaginable surprises awaiting discovery? When humanity first set foot on Proxima Centauri b, we didn't just build a colony. We created a self-sustaining world, entirely different from anything on Earth. Under the ominous red light of the Proxima Centauri dwarf star, every structure faces an extreme challenge to protect against deadly radiation and create a safe space for life to flourish. To overcome this, the ecological shells were born self-sustaining cities, where buildings are not just shelters but living organisms. These massive structures are designed to withstand the radiation from Proxima, with layers of unique energy-absorbing materials and the ability to maintain stable temperatures throughout endless days. Closed-loop systems recycle water, air, and waste, creating a perfect cycle of life without waste. But the creativity doesn't stop there. The vertical gardens and biological farms are not mere crop fields. They are complete ecosystems designed to survive under Proxima's red light spectrum. These plants don't just provide food, they sustain life, creating an environment unlike anything we've seen on Earth. Covered by special glass domes, they harness energy from the red light. Transforming the gardens into vibrant, colorful spaces far beyond what humanity has ever known. Alongside this, groundbreaking energy technology powers the colony. Solar panels are not just designed to absorb sunlight, but are optimized for Proxima's red spectrum, providing energy and serving as shields against the weak light of the star. They not only help the colony sustain its operations, but also serve as shields, efficiently capturing energy from the star's faint light. But energy technology goes beyond just light beneath the planet's surface. Humanity taps into geothermal energy, using the planet's boundless heat to sustain life support systems. And even more mysteriously, technologies now harness the energy from Proxima's solar flares, transforming cosmic events once uncontrolled into powerful energy sources. Could this be the key to unlocking a new energy era? Moving across Proxima b presents another challenge. The dim light and harsh terrain make travel more difficult than ever before. Yet vehicles designed to traverse the planet's surface are equipped with unprecedented technology, allowing them to navigate smoothly in every condition, from bright red fields to deep, dark valleys. These vehicles adapt effortlessly to the constantly changing environment. To stay connected with Earth, an advanced laser communication system has been deployed, despite the vast distance and significant signal delay. What happens when a message from Earth takes months to reach us? Will we feel even more isolated in the vastness of space? Or will we forge a stronger connection than ever before with those who remain behind? As the red light from Proxima Centauri pours down onto Proxima b, the planet transforms into a world utterly unlike any we have ever known. If life exists here, it must have adapted in ways beyond our wildest imagination. Under the strange glow and intense radiation of the red dwarf star, life forms may have evolved entirely different colors and mechanisms, such as deep blacks, purples, or dark oranges, reflecting a perfect adaptation to this alien environment. Trees may no longer be green, instead absorbing red light to generate energy, utilizing a mechanism that science has yet to fully comprehend. Proxima b, a world shrouded in darkness, may harbor a mysterious ecosystem unlike anything we've seen or even dreamed of. But the greater question remains, could there be extraterrestrial life that is capable of communication? If native life exists, what would it look like? Could first contact occur safely, or would it unleash unforeseen dangers? Every decision to engage or avoid these life forms isn't just a scientific matter. It's an ethical one, as each choice could irrevocably alter the future of the colony. To create a suitable environment for humans, scientists have begun exploring biological terraforming, seeding Earth's life forms on Proxima b. They are experimenting with genetically modified microorganisms and plants designed to survive the harsh conditions of the planet. But can we truly modify the environment without upsetting the delicate balance of the planet's natural state? As the pioneers set foot on Dawn Colony, they didn't just build a place to live, they created an entirely new community. One founded on principles completely foreign to anything we've known. The social structure of this colony isn't based merely on Earth's values, but is being shaped by new principles where laws govern not just behavior but also protect life in a harsh, unforgiving world. Every decision, every action is tied to the survival of the community, where collaboration is essential to maintain life itself. The shared values of the colony's community are not solely survival, they embody a deep desire to reach beyond, to explore, and to build something greater. Beneath the red light of Proxima, they share one singular goal: to create a new, independent, and sustainable civilization. But a big question remains: will the residents of Proxima b continue to see Earth as home? Or will they begin to forge a new identity, a Proximan spirit, distinct, independent, and perhaps distant from the world they once knew? Will the solitude beneath Proxima's dim, red light make them feel adrift, or will it foster a stronger sense of community than ever before? Questions about the meaning of life, about the purpose of living on a planet light years away from Earth will inevitably form, driving these new settlers to redefine what it means to be human. The future of Dawn Colony lies in the hands of those building it. Can they maintain long-term life, self-sufficiency, and independence from Earth? Under the red glow of Proxima's dwarf star, humanity will face harsh conditions. Yet it also opens the door to a vast opportunity, a world where anything is possible. The planet holds extraordinary ecosystems, advanced technologies, and untapped mysteries, making it the perfect ground for survival and growth. This vision is not just a product of imagination. Works of science fiction like 2001, A Space Odyssey, and The Expanse have already depicted life beyond Earth, yet Proxima b may be where this reality truly begins. Humanity's desire to reach beyond Earth is an eternal dream. Proxima b, despite its many trials, remains a beacon of hope in the vastness of the universe. Can we truly build a new future in a world so unfamiliar, under the red light of Proxima's distant glow? The questions are immense, but so too is the potential for discovery. The journey to Proxima b is not just about reaching another planet, it's about redefining what it means to be human, to explore, and to create a new chapter in the story of our species. Thanks to powerful telescopes like James Webb and Kepler, astronomers have discovered thousands of exoplanets, worlds orbiting distant stars. Many lie in the so-called habitable zone, where conditions might be just right for life. Dr. Lisa Kaltenegger of Cornell University believes that if Earth-like conditions exist elsewhere, then so might life, even if it's nothing like ours. And beyond science lies something more speculative, and perhaps even more profound. Some futurists and theoretical physicists imagine civilizations that have transcended matter itself. These beings might not need bodies, air, or machines. Instead, they could map the living architecture of the universe using sacred mathematical patterns, the golden ratio, cosmic spirals, the primal geometry of existence. The search for extraterrestrial life is not just a scientific pursuit. It's a quiet, persistent whisper from the human soul, asking the oldest question we know: are we truly alone? Long before rockets pierced the sky or satellites circled Earth, our ancestors looked up with a sacred sense of awe, as if the heavens weren't just filled with stars, but served as the ceiling of a vast, invisible spirit world. It was Galileo Galilei, with one of the first telescopes, who cracked open that celestial window. When he spotted dark patches on the moon's surface, he believed they were oceans, possibly teeming with life. It may have been a misinterpretation, but it marked a profound turning point. Science was stepping out of myth and into possibility. Then came Immanuel Kant, the great philosopher, who imagined a cosmos organized by levels of intelligence. In one of his more speculative hypotheses, he proposed that the farther a planet was from the sun, the more intelligent its inhabitants would be. In his view, the sun's intense light dulled thought, while distant, dimmer worlds might allow consciousness to flourish into something nearly divine. Today we know those early ideas were scientifically inaccurate. But the deeper question they sparked still burns. Is someone out there thinking about us? These ancient visions didn't just search for life, they searched for meaning. And from those first primitive lenses to the observatories of today, our journey has never been just about discovery, it's been about identity. We've walked on the moon, roved the red sands of Mars, sent probes to frozen moons and ancient asteroids. And yet, despite decades of exploration, we have not found a single living being in our solar system. At least, that's what the data tells us. But have we really seen everything there is to see? Or did something once exist only to vanish long before we arrived? One of the more controversial, yet strangely compelling, hypotheses suggests that the moon may have once hosted an ancient civilization. Those dark plains that Galileo mistook for lunar seas? Perhaps they are not oceans at all, but graveyards of a golden era lost to time. Some theorists believe this civilization could have collapsed in a catastrophic war or as the result of uncontrolled energy experiment. It's not entirely baseless. Plasma physicist Dr. John Brandenburg once cited evidence of unusual radioactive elements on Mars, pointing to the possibility of an ancient nuclear detonation of non-terrestrial origin. And then there's Jupiter, the gas giant with a magnetic field nearly 20,000 times stronger than Earth's. Astrophysicists like Dr. Kevin Baines at NASA have speculated that such an immense field could serve as a natural prison for high-energy life forms. Beings composed not of cells and carbon, but of plasma or electromagnetic force. We haven't found life in the solar system, but maybe we're not looking the right way. Maybe the truth isn't on the surface. It's buried deep, shielded from our instruments, hidden within the very structure of space itself. And while data may not yet reveal it, our imagination keeps knocking, asking to be let in. Thanks to advanced telescopes like Kepler, TESS, and especially the James Webb Space Telescope, we are now entering a golden age of astronomy. For the first time in human history, we're not just speculating about planets beyond our solar system, we're actually seeing them. Thousands of worlds have been confirmed, many similar in size to Earth, and a surprising number of them orbit within what scientists call the habitable zone, not too hot, not too cold, and potentially capable of supporting liquid water. Among the most intriguing candidates is TOI 715b. A rocky exoplanet located about 137 light-years from Earth. With a radius about 1.5 times larger than our own planet, and orbiting a cool red dwarf star, TOI 75b lies in an ideal range for habitability. It's currently one of the top targets in our search for signs of life. But here's the catch. The light we're seeing from TOI 715b today actually left the planet 137 years ago. In our search for life beyond Earth, humanity keeps returning to the same familiar checklist. Liquid water, biosignature gases, the Goldilocks zone, that sweet spot around a star, where temperatures are just right for life as we know it. We scan for traces of methane, oxygen, or signs of ancient microbes. As though the universe were obligated to follow the same biological script written here on Earth. But what if they, extraterrestrial beings, don't breathe air, don't need water, and don't even exist within the three-dimensional space we inhabit? What if life could exist without a body, without cells, without breath, yet still thrive? Scientists are starting to open up to these possibilities. As Dr. Sarah Seeger of MIT puts it, we may be missing the signals because we're only searching within our narrow band of understanding. One of the most intriguing clues in recent years has come from K2-18b, a planet roughly 120 light-years away. Observations by the James Webb Space Telescope detected water vapor in its atmosphere, alongside dimethyl sulfide, DMS, a compound that on Earth is produced only by marine organisms. This may be a faint greeting from a distant ocean, a place where mythic-like beings, perhaps the leviathans of ancient stories, silently drift beneath thick clouds and restless waves. Entire planets covered in water could host forms of life we've never imagined, creatures born of crushing pressure, eternal darkness, and heat from the planet's core, not sunlight. Some speculative biologists have called them biological leviathans, enormous lords of the deep, ancient in intellect and alien in every sense. And so our search for life is evolving into a deeper challenge, a race against the limits of our own imagination. We've launched spacecraft to the edge of our solar system, scanned thousands of distant planets with colossal telescopes, and decoded the faint glow of stars hundreds of light years away. Yet everything we know about the universe, about life, still amounts to little more than a speck of dust in an infinite desert. But humanity doesn't stop at the boundaries of the known. The search for extraterrestrial life is not just a scientific endeavor, it's a quiet yearning from the deepest part of who we are. In a cold and silent cosmos, where distances are measured in light years and silence can last millennia, we send out a call, not only to ask, is anyone out there, but to say, we are here, please hear us, to know, in some fundamental way, that we are not alone. Scientists like Carl Sagan once said, the universe would be a pretty big waste of space if it's just us. Will humanity be ready to face a consciousness far beyond ours? A truth that could shatter our religions, our beliefs, even our concept of what it means to be human? Maybe this journey isn't just about finding someone else. Maybe it's about rediscovering ourselves, reflected in the eyes of something completely unfamiliar. That horizon is expanding. And the real question is no longer, is there life out there? It's this, when that life answers, will we be ready to listen? What would happen if, one day, the familiar moon in our sky suddenly disappeared and was replaced by another moon from within the system? It could be Io, Jupiter's moon. Extreme tidal forces would immediately compress Earth's crust, triggering devastating earthquakes. A Titan with an atmosphere so dense it would swallow sunlight, pushing humanity into eternal winter. Thick hydrocarbon haze, or Ganymede, where tidal effects would raise walls of water hundreds of meters high. Ready to erase every coastal city within a single rotational cycle. In the solar system, no celestial body demonstrates the raw brutality of gravity more clearly than Io, continuously flexed and distorted with every orbit around Jupiter. Its surface swells and collapses by hundreds of meters. Io is subjected to extreme stretching from Jupiter, combined with a stable orbital resonance with Europa and Ganymede. As a result, Io has become the most volcanically active body ever known. More than 400 active volcanoes, silicate lava flows exceeding 1,200 degrees Celsius, and eruption plumes rising hundreds of kilometers high. Its entire surface is constantly renewed on timescales of just a few million years. So, what would happen if Io were to replace Earth's moon? In theory, a similar orbital distance would mean Io's average gravitational pull on Earth would not differ dramatically from that of our current moon, but Io carries with it a tidal force pattern that varies strongly over time, driven by its slightly eccentric orbit and its own internal resonant interactions. When Io pulls on Earth, that force would be uneven, unstable, and impossible to be gently absorbed by the mantle and oceans as today. Imagine Earth being subtly but continuously bent, not by a few centimeters as it is now, but enough to accumulate stress within the mantle and lithosphere. The additional tidal energy would significantly increase Earth's internal heat flow, which today stands at about 47 terawatts. Even a modest increase by planetary standards would trigger cascading geological consequences. Earthquakes would become more frequent, subduction zones more violent, magma chambers would recharge faster. Hidden beneath an ice sheet roughly 15 to 25 kilometers thick lies a global ocean, tens to more than 100 kilometers deep, holding more water than all of Earth's oceans combined. This ocean does not freeze in the cold of space because Europa is continuously warmed from within. Europa orbits Jupiter with a period of about 3.55 days. Thermal models show that tidal heating is powerful enough to keep water in a liquid state for billions of years. Despite surface temperatures near minus 160 degrees Celsius, it is just enough energy to sustain an ocean, but not enough to turn the surface into a hellscape. But if Europa were to replace Earth's moon, that just enough would instantly become too much. Placed in the role of Earth's satellite, the increased tidal forces would not only raise and lower sea levels, but also trigger planet-scale action within the deep oceans. On today's Earth, most tidal energy is dissipated along continental shelves and narrow straits, with a total power output of only a few terawatts, but as tidal amplitudes grow and oscillations become more frequent, the dissipated power rises non-linearly. The result is not merely higher tides, but oceans warming from within, driven by a broadly distributed and difficult-to-control heat source. Rising internal ocean heat would disrupt thermohaline circulation, breaking the ocean conveyor belts that have stabilized Earth's climate for tens of thousands of years. Stronger currents would erode coastlines worldwide, thinning continental shelves that serve as some of the planet's most important biological buffers. At the same time, increased tidal stress along continental margins would stimulate tectonic activity, not in explosive bursts like Io, but in a persistent, widespread, and unpredictable manner. Among all the moons in the solar system, Ganymede stands out as a troubling exception. It is not only the largest moon orbiting Jupiter, but the largest moon ever known. So what would happen if Ganymede were to replace Earth's moon? With a mass greater than our current moon, Ganymede's gravity would increase the braking torque acting on Earth, leading to an exchange of rotational momentum. Earth would lose its rotational speed more rapidly, causing days to lengthen at a rate far greater than what we experience today. Biological cycles tightly bound to the day-night rhythm would be stretched over much shorter geological timescales than expected. Tides would also grow stronger, not explosively like Io, nor quietly like Europa, but in a steady and heavy manner. Increased tidal amplitude would lead to greater energy dissipation within the oceans and the mantle above. Earth would enter a new evolutionary regime, one in which gravitational energy is pumped into the system at a stable yet elevated level beyond familiar thresholds. However, Ganymede's true danger lies in its magnetic field. Earth today is protected by a strong magnetosphere generated by the motion of its liquid metallic core. When Ganymede, a moon with its own intrinsic magnetic field, is placed near Earth, the two magnetospheres would begin to interact, not by merging, but by overlapping, colliding, and constantly restructuring. The result would be localized weakening of radiation shielding. High-energy particles could penetrate deeper into the upper atmosphere, accelerating ionization, disrupting ozone chemistry, and altering the thermal balance of the middle atmosphere. This is a subtle threat, marked not by sudden catastrophe, but by gradually increasing radiation, climate cycles slipping out of phase, and unfamiliar evolutionary pressures placed on the biosphere. Species that depend on long-term stability, especially complex life, would be forced to adapt in an environment no longer electromagnetically quiet. Ganymede demonstrates that size and complexity do not equal safety. If Earth were to host a moon like Ganymede, our planet would not die immediately, but it would slowly become a more unpredictable world. Longer days, altered radiation environments, after the early phases of accretion and outgassing, Earth's primordial atmosphere was dominated by carbon dioxide, methane, nitrogen, and water vapor, with almost no free oxygen. This was a transitional state, appropriate for a young planet at a time when the Sun was 25 to 30% weaker than it is today. Under those conditions, life emerged without oxygen, without intense sunlight, existing at microscopic scales. For more than 1.5 billion years, Earth was a planet of anaerobic organisms. They evolved slowly, but continuously, gradually altering the chemistry of the oceans and the atmosphere in ways that were almost impossible to detect over short timescales. Around 2.4 billion years ago, an evolutionary threshold was crossed, the Great Oxidation Event. Oxygen, a byproduct of photosynthesis, accumulated beyond the absorption capacity of oceans and rocks and began to spread into the atmosphere. This was not an immediate improvement, but a planetary crisis. Many anaerobic organisms were wiped out, and ecosystems collapsed on a massive scale. Today, Earth's atmosphere is astonishingly thin and fragile. More than 99% of its mass is confined within a layer less than 30 kilometers thick, compared to the planet's radius of over 6,300 kilometers. Yet this delicate shell is the result of billions of years of biological, geological, and chemical evolution, and it continues to change. The atmosphere is not permanently stable. It is maintained in a state of dynamic balance, where life constantly adjusts its chemical composition through photosynthesis, respiration, and the nitrogen and carbon cycles. When atmospheric composition shifts, the fastest responding system is not the oceans or the deep geology, but the climate, the shortest-term evolutionary mechanism, yet one with immediate planet-wide consequences. Earth's climate has never evolved along a straight line. Instead, it has oscillated continuously, swinging between climatic extremes from worlds tens of degrees Celsius warmer than today to intervals of cold so severe that the planet nearly froze over entirely. Geological records reveal that Earth's climate has repeatedly approached the brink of collapse. Around 720 to 635 million years ago, the planet may have entered a snowball Earth state, when ice covered nearly the entire surface. The reflective power of ice reduced heat absorption, causing cold conditions to reinforce themselves through a positive feedback loop that pushed the climate system toward its limits. By contrast, during super greenhouse periods such as the Cretaceous, climate evolved in the opposite direction. Global average temperatures rose 10 to 14 degrees Celsius above present levels, sea levels climbed by tens of meters, and permanent ice at both poles vanished. These states did not emerge suddenly. They developed over millions of years through the accumulation of CO2, the rearrangement of continents, and shifts in ocean circulation. Climate is shaped by many forces: Earth's orbit and axial tilt, solar radiation, plate tectonics, and atmospheric composition. When climate cools rapidly, habitable environments contract. Organisms are forced to optimize their metabolism, migrate toward refuges, or form new symbiotic relationships. When climate warms abruptly, new ecological niches appear, but oceans acidify, oxygen levels decline, and food webs grow fragile. Each climatic swing is therefore not merely an environmental change, but an evolutionary trial. Seen from space, very few planets manage to preserve conditions suitable for complex life through billions of years of such fluctuations. And it is within these repeated cycles of instability that Earth entered a new phase of its evolution, one in which life no longer merely responds to climate, but begins to act back upon the planet itself. Over hundreds of millions of years, marine organisms such as foraminifera, coccolithophores, and corals have continuously precipitated calcium carbonate, forming thick limestone layers on a continental scale. This is the result of long-term biological repetition, in which carbon is transferred from the oceans and atmosphere into Earth's crust. On land, a similar process occurred during the Carboniferous period, roughly 360 to 300 million years ago. Ancient forests expanded faster than biological decomposition could keep pace, causing large amounts of carbon to be buried as coal. This accumulation reduced atmospheric CO2 levels, driving global climate change and triggering new evolutionary feedbacks. Even soil, the foundation of terrestrial ecosystems, is the product of a long-term biogeological evolutionary process. Microorganisms, fungi, and plant roots gradually broke down bedrock, releasing minerals and forming porous structures that retain water and nutrients. Soil did not appear instantly. It formed over millions of years through interactions between life and rock. At the chemical level, nitrogen-fixing bacteria gradually converted inert N2 gas into biologically usable forms, laying the foundation for global food chains. Sulfur processing microorganisms controlled redox reactions in oceans and sediments, exerting long-term influence on seawater composition and the atmosphere. These processes unfold slowly and almost invisibly, but when accumulated over geological time, they shape how the planet operates. Geological history shows that Earth has repeatedly entered phases of comprehensive restructuring, when the influence of the biosphere reached a threshold large enough to drive changes in climate and ocean chemistry. Accumulated pressures were eventually released through mass extinctions, abrupt climate shifts, or large-scale reorganization of the biosphere. It is precisely during these moments that the system of life was effectively reset, opening pathways for new forms of life to emerge. It is the history of a planet where life gradually became a geological force, evolving alongside geology through billions of years of change. Over the past 540 million years, science has identified 5 major mass extinctions, each wiping out between 70% and more than 90% of all living species. In planetary evolution, these events function as phase transitions, moments when the structure of life is dismantled and reorganized. The late Ordovician extinction, around 440 million years ago, offers an early example of how climate gradually pushed the biosphere toward a critical threshold. As Earth cooled rapidly, ice accumulated at the poles, causing sea levels to fall. Most life at the time depended on shallow seas environments that vanished within a short geological window. Tens of millions of years of evolution were erased. Yet, at the same time, empty ecological niches began to form, opening pathways for new evolutionary directions during the Silurian period. The greatest biological catastrophe in Earth's history occurred at the Permian-Triassic boundary, roughly 252 million years ago. The pressure did not come from a single cause, but from the prolonged accumulation of continent-scale volcanic activity in Siberia. Over hundreds of thousands of years, vast amounts of CO2 and toxic gases were released, driving rapid global warming, widespread ocean deoxygenation, and severe acidification. Ecosystems collapsed in cascading failure. It took nearly 10 million years for the biosphere to recover comparable levels of diversity, but when life returned, it had evolved into a different structure. Reptiles became dominant, laying the foundation for the age of dinosaurs. By the time of the end Cretaceous extinction, 66 million years ago, Earth's evolution revealed a different kind of restructuring, one driven by an instantaneous shock. An asteroid roughly 10 to 12 kilometers in diameter struck the Yucatan Peninsula, releasing enormous energy. Within hours to days, the planet entered a state of chaos. Over months to years, dust and aerosols filled the sky, temperatures plunged, and photosynthesis nearly ceased. Creatures that had dominated for over 150 million years, the dinosaurs, disappeared. Yet, within that evolutionary vacuum, small mammals with rapid adaptive capacity gradually expanded and diversified explosively over the following millions of years. On a planetary scale, extinction does not end evolution. It resets its trajectory, allowing life to continue in a new structural form. In the past, mass extinctions were always triggered by forces external to the biosphere: climate shifts, volcanism, or asteroid impacts. But Earth's evolution is now entering a phase without historical precedent. Throughout Earth's evolutionary history, no species has ever driven planetary change as rapidly as humans. In just a few centuries, we have altered the climate, biological cycles, and global landscapes at a pace far exceeding the tempo of natural evolution. The world's population has grown from roughly 1 billion people in 1800 to more than 8 billion today. Alongside this growth has come an unprecedented expansion of resource extraction, industrialization, and land use change. More than 75% of the planet's ice-free land surface has been transformed by agriculture, urbanization, and infrastructure. Rivers have been dammed, sediment flows altered, reshaping coastlines and downstream ecosystems. These changes are no longer local in nature. They intervene directly in Earth's evolutionary cycles. Many scientists argue that we are now witnessing the onset of a sixth mass extinction, not driven by asteroids or supervolcanoes, but by a single species. What is without precedent is that this agent of change possesses the ability to recognize its own role. Technology has allowed humanity to escape many direct biological pressures, disease, extreme climates, food scarcity, while simultaneously amplifying our impact on the Earth system. For the first time, biological evolution, technological evolution, and planetary evolution are unfolding together at the same moment. Some researchers propose that Earth has entered a new epoch. The Anthropocene, the age of humans. Humanity is no longer merely adapting to Earth. We are forcing Earth to adapt to us. The boundary between a lasting evolutionary turning point and a thin sedimentary layer in the geological record may depend on how humanity understands and responds to this new role. Will we become a stable component of planetary evolution, or the trigger for Earth's next great restructuring? Earth's existence is not a cosmic accident, but the result of a resilient self-regulating process spanning 4.54 billion years. From the interaction of tectonic plates and ocean circulation to the planet's fragile atmosphere, all of these elements have formed a unified biogeochemical system that functions like a living entity. Within that system, life is not merely a passive presence. It acts as an architect, reshaping the chemical composition of the atmosphere and establishing new energy cycles. It is this tightly bound symbiotic relationship that has allowed the planet to maintain a state of dynamic balance amid the harsh fluctuations of space. The Earth we see today stands as evidence of a parallel evolutionary journey. The planet created the conditions for life, and life, in return, shaped a world uniquely capable of enduring within the quiet vastness of the solar system. What would happen if, one day, the familiar moon in our sky suddenly disappeared and was replaced by another moon from within the solar system? It could be Io, Jupiter's moon, whose extreme tidal forces would immediately compress Earth's crust, triggering devastating earthquakes. A Titan with an atmosphere so dense it would swallow sunlight, pushing humanity into an eternal winter beneath a thick hydrocarbon haze. Or Ganymede, where tidal effects would raise walls of water hundreds of meters high, ready to erase every coastal city within a single rotational cycle. Each moon is a world unto itself, an entity capable of destruction or creation. Gravitational models and orbital dynamics reveal that changing only the mass or distance of a moon is enough to push the entire Earth system into a completely different state. And now, we begin a journey into the most extreme scenarios. In the solar system, no celestial body demonstrates the raw brutality of gravity more clearly than Io, continuously flexed and distorted with every orbit around Jupiter. Its surface swells and collapses by hundreds of meters. Io is subjected to extreme stretching from Jupiter, combined with a stable orbital resonance with Europa and Ganymede. As a result, Io has become the most volcanically active body ever known. More than 400 active volcanoes, silicate lava flows exceeding 1,200 degrees Celsius, and eruption plumes rising hundreds of kilometers high. Its entire surface is constantly renewed on timescales of just a few million years. So, what would happen if Io were to replace Earth's moon? In theory, a similar orbital distance would mean Io's average gravitational pull on Earth would not differ dramatically from that of our current moon. But Io carries with it a tidal force pattern that varies strongly over time, driven by its slightly eccentric orbit and its own internal resonant interactions. When Io pulls on Earth, that force would be uneven, unstable, and impossible to be gently absorbed by the mantle and oceans as they are today. Imagine Earth being subtly but continuously bent, not by a few centimeters as it is now, but enough to accumulate stress within the mantle and lithosphere. The additional tidal energy would significantly increase Earth's internal heat flow, which today stands at about 47 terawatts. Even a modest increase by planetary standards would trigger cascading geological consequences. Earthquakes would become more frequent, subduction zones more violent, magma chambers would recharge faster, and volcanoes would shift from pressure release to forced energy discharge. In the oceans, tsunamis would no longer be rare events caused by earthquakes or asteroid impacts, but a secondary consequence of a planet being constantly yanked and strained. Coastlines would become permanently unstable regions. What must be emphasized is that extreme tidal forces do not create complex life. They destroy the foundations required for such life to persist. Io offers us an uncomfortable but unmistakable lesson. Gravitational energy, when not regulated by the right orbital architecture, becomes a destructive force rather than a creative one. Earth today has volcanoes, earthquakes, and plate tectonics, but all of them operate within a range of variation that has allowed complex life to exist for hundreds of millions of years. Replacing the moon with Io would mean stepping far outside that range. Io is proof that a world can be overflowing with energy and yet be entirely uninhabitable. And if a single satellite that is too violent is enough to shatter geological balance, then what happens when we turn to a moon less explosive than Io Europa, where tidal energy does not erupt at the surface, but is trapped within dark, deep oceans beneath a shell of ice? Hidden beneath an ice shell roughly 15 to 25 kilometers thick lies a global ocean, tens to more than 100 kilometers deep, holding more water than all of Earth's oceans combined. This ocean does not freeze in the cold of space because Europa is continuously warmed from within. Europa orbits Jupiter with a period of about 3.55 days. Thermal models show that tidal heating is powerful enough to keep water in a liquid state for billions of years, despite surface temperatures near minus 160 degrees Celsius. It is just enough energy to sustain an ocean, but not enough to turn the surface into a hellscape. But if Europa were to replace Earth's moon, that just enough would instantly become too much. Placed in the role of Earth's satellite, the increased tidal forces would not only raise and lower sea levels, but also trigger planet-scale friction within the deep oceans. On today's Earth, most tidal energy is dissipated along continental shelves and narrow straits, with a total power output of only a few terawatts. But as tidal amplitudes grow and oscillations become more frequent, the dissipated power rises non-linearly. The result is not merely higher tides, but oceans warming from within, driven by a broadly distributed and difficult to control heat source. Rising internal ocean heat would disrupt thermohaline circulation, breaking the ocean conveyor belts that have stabilized Earth's climate for tens of thousands of years. Stronger currents would erode coastlines worldwide, thinning continental shelves that serve as some of the planet's most important biological buffers. At the same time, increased tidal stress along continental margins would stimulate tectonic activity, not in explosive bursts like Io, but in a persistent, widespread, and unpredictable manner. Climate would not collapse within a single generation, but would shift into new states hotter, wetter, and more variable before life has time to adapt. Europa, acting as Earth's moon, would erode the very thing that has sustained us, slow stability. Climate variations driven by orbital cycles would become stronger and faster. Ecological boundaries would shift continuously. As we leave Europa, we carry with us a sobering realization. Stability is not a natural state, but a rare privilege. And if a larger satellite with stronger gravity, perhaps even its own magnetic field like Ganymede, were to assume the role of the moon, would that fragile stability have any chance at all? Among all the moons in the solar system, Ganymede stands out as a troubling exception. It is not only the largest moon orbiting Jupiter, but the largest moon ever known. So what would happen if Ganymede were to replace Earth's moon? With a mass greater than our current moon, Ganymede's gravity would increase the braking torque acting on Earth, leading to an exchange of rotational momentum. Earth would lose its rotational speed more rapidly, causing days to lengthen at a rate far greater than what we experience today. Biological cycles tightly bound to the day-night rhythm would be stretched over much shorter geological timescales than expected. Tides would also grow stronger, not explosively like Io, nor quietly like Europa, but in a steady and heavy manner. Increased tidal amplitude would lead to greater energy dissipation within the oceans and the mantle above. Earth would enter a new evolutionary regime, one in which gravitational energy is pumped into the system at a stable yet elevated level beyond familiar thresholds. However, Ganymede's true danger lies in its magnetic field. Earth today is protected by a strong magnetosphere generated by the motion of its liquid metallic core. When Ganymede, a moon with its own intrinsic magnetic field, is placed near Earth, the two magnetospheres would begin to interact. Not by merging, but by overlapping, colliding, and constantly restructuring. The result would be localized weakening of radiation shielding. High-energy particles could penetrate deeper into the upper atmosphere, accelerating ionization, disrupting ozone chemistry, and altering the thermal balance of the middle atmosphere. This is a subtle threat, marked not by sudden catastrophe, but by gradually increasing radiation, climate cycles slipping out of phase, and unfamiliar evolutionary pressures placed on the biosphere. Species that depend on long-term stability, especially complex life, would be forced to adapt in an environment no longer electromagnetically quiet. Ganymede demonstrates that size and complexity do not equal safety. If Earth were to host a moon like Ganymede, our planet would not die immediately. But it would slowly become a more unpredictable world. Longer days, altered radiation environments, and a climate more sensitive to small disturbances. And if a satellite that is simply too large can already cause such subtle problems, what would happen if Earth had to share its orbit with a moon that is not only massive, but also possesses its own atmosphere like Titan? Not only is Titan the largest moon of Saturn, with a surface pressure about 1.5 times that of Earth, it is, in a sense, even more air-heavy than our own planet. And it is precisely this seemingly harmless trait that opens an entirely new and unstable scenario if Titan were to replace the moon. Titan has a diameter of about 5,150 kilometers, slightly smaller than Ganymede, yet nearly 1.8 times more massive than Earth's moon. Its gravity is strong enough to retain a nitrogen-rich atmosphere, mixed with methane and a wide array of complex organic compounds. Instantly, Earth would no longer be a planet with a single atmosphere. We would have two large bodies at close range, each wrapped in its own gaseous envelope. With a mass greater than the current moon, This satellite's gravity would generate atmospheric tides far stronger than those we experience today. Planet-scale pressure waves would propagate through Earth's mesosphere and thermosphere, altering wind circulation and disrupting stable structures such as the jet streams. But Titan does not merely pull. It also reflects, absorbs, and re-emits solar radiation in ways profoundly different from Earth. Titan's thick, hydrocarbon-rich atmosphere is a chemical engine highly sensitive to ultraviolet light. Placed closer to the sun, photochemical reactions would accelerate, producing even more organic aerosols. These hazes would not only blanket Titan, but could be stretched and dispersed into near-Earth space, altering the plasma environment and radiation conditions around the Earth-Titan system. The result is that Earth's atmospheric circulation would begin to feel indirect influence from another world, generating climate phases that are difficult to predict and no longer repeat with the regularity of familiar Milankovitch cycles. With Titan as a satellite, Earth would not collapse overnight, but societies dependent on weather forecasting, seasonal agriculture, and ecological stability would face a planet that is harder to read, harder to predict, and harder to adapt to. When Earth has an atmospheric moon, our planet becomes a place where even small disturbances can resonate and amplify through continuous oscillations. In the universe, there are worlds that become more chaotic the richer they are. And there are worlds like Earth today that survive precisely because they do not have to share their atmosphere, cycles, and rhythms with anyone else. Yet Titan still orbits in the same direction, stable and at least not opposing Earth's rotation. So what would happen if our satellite not only had an atmosphere, but also moved in reverse like Triton? An irreversible erosion of angular momentum would begin. With a retrograde orbit, everything happens faster. Torque acts against Earth's rotation, extracting rotational momentum at an accelerating rate. Dynamical models show that a retrograde satellite at a distance comparable to today's moon would cause Earth to lose rotational momentum far more rapidly than in a prograde scenario. Days would lengthen not over billions of years, but on much shorter geological timescales, fast enough to disrupt a biosphere effectively programmed around a stable day-night rhythm. This change would not require surface violence. It would occur within the mechanical foundation of the Earth satellite system itself. But it does not stop there. Instead of slowly drifting outward like our current moon, Triton in the Neptune system is gradually spiraling inward on an inevitable path toward destruction or collision. If Triton orbited Earth, its orbit would either shrink until it crossed the Roche limit and was torn into a ring of debris, or it would progress toward a catastrophic merger. In both cases, Earth would have no stable future. A dense debris ring would trigger prolonged meteor bombardment, while a direct impact would restructure the planet's surface, erasing any complex biosphere that might exist. Data from Voyager 2 reveal that Triton exhibits cold geological activity, nitrogen geysers, and youthful terrain, suggesting an internal energy source, likely tied to orbital decay and internal restructuring following its capture. If Triton were to replace the Moon, Earth would inhabit a system whose future is inherently short-lived because of flawed orbital architecture. A biosphere may adapt to warmer or colder climates, but it struggles to adapt to a mechanical foundation that is steadily collapsing. Long cycles from ocean circulation and glaciation to biological evolution all require a stable stage. Triton demonstrates that formation history matters just as much as present conditions. A captured satellite may be beautiful, may be active, but it is rarely a sound foundation for the long-term habitability of its host planet. As we leave Triton behind, we realize that not every moon is a companion. Some are orbital saboteurs, carrying a deferred cost paid in momentum and stability. And if a retrograde orbit is too dangerous because it interferes too much, what happens at the opposite extreme, when a satellite is so small that Earth nearly loses its tides altogether, as with Phobos? From about 419 to 359 million years ago, the Devonian is often called the Age of Fish because fish came to completely dominate the oceans. Jawed fish exploded in both number and form, occupying every layer of the water column, from shallow seas to deeper zones. The Devonian oceans were no longer relatively stable open spaces, but harsh arenas of competition, where size, speed, and power determined survival. At the top of the food chain stood Dunkleosteus, one of the most terrifying predators ever to exist, reaching an estimated length of 6 to 8 meters. Dunkleosteus did not have teeth in the conventional sense, but instead possessed razor-sharp bony plates that closed with a bite force of around 6,000 newtons, powerful enough to crush most contemporary organisms. Alongside it, ancient sharks, such as Cladocellae, represented a very different evolutionary path: light, fast, and agile, without heavy armor or enormous size. Cladocellae which had a streamlined body that allowed it to pursue prey over long distances. While the oceans grew ever more dangerous, life on land underwent a profound transformation. The Devonian was the period in which the first forests appeared. Plants were no longer limited to small, low-growing forms clinging to the ground. For the first time, trees developed true roots, woody trunks, and leaves, rising upward to compete for light. These early forests fundamentally reshaped Earth's surface. Roots stabilized soils and reduced erosion, forming rich layers. Large-scale photosynthesis increased atmospheric oxygen, and the global carbon cycle was restructured at a planetary scale. The emergence of forests also triggered an indirect but revolutionary consequence. Terrestrial environment too much, and Earth is torn apart. Complex life exists only within a very narrow range between these extremes. While one remarkable evolutionary branch in the oceans began to experiment with something unprecedented, bridging the worlds of water and land. Around 375 million years ago, a creature called Tiktaalik rossi appeared in shallow, swampy environments. It had gills, but also primitive lungs, fins, but with internal bone structures resembling limbs, strong enough to support its body against the bottom. And most importantly, a flexible neck that allowed its head to move independently of its torso. Tiktaalik demonstrated that the vertebrate body plan was ready for this transition. The Devonian therefore stands as an age of shifting power. When the Devonian came to an end, Earth was prepared for a new era, the Carboniferous period, when oxygen levels would surge, swamp forests would blanket the continents, and the planet would enter a truly gigantic world. Enceladus has a diameter of only about 504 kilometers, nearly 7 times smaller than Earth's moon, and a mass roughly 1/100,000th of the moon. With such a small mass, Enceladus's gravity is almost incapable of generating meaningful tides on Earth, even if it were placed at the same orbital distance as today's moon. This leads to the first and most critical consequence. Enceladus cannot stabilize Earth's axial tilt. Earth's 23.4-degree axial tilt, the foundation of stable seasons and long-term climate cycles, is maintained by the combined inertial balance between Earth and a sufficiently massive satellite. Climate models show that if axial tilt fluctuates by just a few additional degrees over short geological timescales, climate belts would shift rapidly enough to place severe stress on the biosphere. Ice ages could advance or retreat outside familiar rhythms. Ecosystems would lack the time needed to adapt, and civilizations dependent on seasonal stability would face a far more unpredictable Earth. Second, Enceladus is also incapable of regulating long-term climate cycles. Weak tides mean the oceans lose a critical source of mechanical mixing. As a result, the climate becomes more prone to extreme states, hotter or colder, and less able to return to equilibrium. Enceladus possesses enough tidal energy to sustain a subsurface ocean within itself, but it is entirely insufficient to maintain the dynamical stability of a planet like Earth. That energy is almost completely dissipated inside Enceladus, released through the tiger stripe fractures at its south pole. This makes one point clear: biological potential does not equal planetary dynamical function. Earth requires a partner that is massive enough, stable enough, and dynamically quiet enough not to disrupt long-term cycles. Life might arise, but struggle to persist. Intelligence might spark, but find it difficult to endure. Enceladus is like a perfect laboratory, built upon a foundation that is simply too weak. So, which moon is truly good for Earth? And why is our current moon, imperfect as it may be, such a remarkably rare balance? Not because Earth's moon is perfect, but because it sits precisely at the fragile intersection of some of the strictest physical limits. The moon accounts an unusually large ratio by planet-satellite standards in the solar system. It is this very anomaly that creates its advantage. The moon is massive enough to generate significant inertial torque, stabilizing Earth's axial tilt around 23.4 degrees. Observations of the present Earth confirm that lunar tides are strong enough to mix the oceans and sustain coastal nutrient cycles, yet not strong enough to trigger global geological instability. The moon orbits at an average distance of about 384,400 kilometers, close enough for tidal forces to remain effective, yet far enough to avoid destructive scenarios. Moreover, the moon's orbit is nearly circular and prograde relative to Earth's rotation. This ensures a gentle exchange of angular momentum. Earth's day lengthens very slowly, while the moon recedes at a rate of only a few centimeters per year. One decisive factor is that the moon lacks a thick atmosphere. It does not reflect, absorb, or re-radiate energy in unpredictable ways. The moon influences Earth through gravity alone, a form of interaction that is quiet, predictable, and stable over time. Earth retains control over its own magnetosphere, undisturbed by a nearby secondary magnetic system. The sun provides energy, but the moon shapes rhythm. Without stable rhythm, energy becomes chaos. With rhythm, energy becomes the foundation for life. If changing just one satellite is enough to collapse a balance maintained for billions of years, how fragile is our existence? The moon is not a romantic symbol. It is a dynamical pillar supporting the biological history of our planet. So when we ask, which moon is best for Earth? The answer lies in recognizing that we already possess a rare balance, not perfect in isolation, but optimal as a whole. Swapping the moon is not simply a matter of replacing one celestial body with another. It is a process that restructures the entire dynamical system of our planet. Through simulations, it becomes clear that most satellites in the solar system possess incompatible traits. Either they are too small to sustain tidal rhythms, or they carry extreme gravity and unstable orbits capable of disrupting Earth's axial tilt and global climate. Our current moon may not be a theoretically perfect object, but it maintains a balance that is extraordinarily rare in the universe. It has enough mass to stabilize Earth's tilt, enough distance to regulate the oceans, and enough long-term stability to accompany our planet for billions of years. This leads to an essential realization. Complex life on Earth is not only the result of a Goldilocks position relative to the Sun, but also a direct consequence of having the right kind of satellite one with the right mass, the right orbit, and the right timing in evolutionary history. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.